So today we'll be picking up in what we talked about before. There are three major spectroscopy methods organic chemists use to decide the structures of an unknown molecule. So we went over the proton NMR, which tells you lots of information. Well, not just proton NMR, but it tells you lots of information like chemical shift or what's the relative environment your proton is feeling. Number of peaks, that tells you the number of chemically equivalent hydrogen. We have integration, that tells you the ratio between those chemically equivalent hydrogen atoms, and also the splitting pattern. So that's for the NMR. We spend lots of time before your second midterm go over topics on proton NMR. And then in our last lecture, we went over IR spectroscopy or infrared spectroscopy. And we went over the basic of infrared spectroscopy. What it's doing is your atom is continuously vibrating at room temperature. And we use light to probe those energy differences between different vibrational states in your molecule. And IR vibrational frequency or IR spectroscopy is normally used to decide whether or not you have some specific functional group. So we went over two most iconic peaks in your IR spectroscopy, namely the OH stretching, which is over 3,000 wave number. It's really broad and big peak on your IR spectrum. And then also the carbonyl absorption peak around 1,700 on your IR spectrum. That's really sharp and also intense peak. So by looking at your IR spectroscopy, you're not going to be able to identify every peak, but you can figure out some useful information by looking at the spectrum. So mass spectrometry normally works similarly like IR. You'll have lots of peaks. It is not always possible to assign a peak to all your mass spectrometry signals. So let's look at our mass spectrometry. So before we get started, what are the information we're trying to get in mass spectrometry? Well, it's called mass spectrometry. So we're getting information about the mass of a molecule. So let's go over, again, the structure is the same. We'll go over first the theoretical background and also how your spectrometer is set up. And then we'll look at an example mass spectrometry, mass spectrum together and try to find out what are the information you can get by looking at that mass spectrum. And then we'll do some practice problem together and see how does mass spectrometry help us understanding the molecular structure of an unknown organic molecule. So, first thing, theoretical background. So this is a crude sketching of what is happening in your mass spectrometer. So what's happening is imagine you have an unknown neutral molecule. Well, it can be any kind of molecule imagined, just a random organic molecule. We feed that organic molecule into the mass spectrometry machine, and what that machine is going to do is it's going to shoot like high energy electron beam to break off your neutral molecule into different fragments. All right, so what it's doing is imagine you have a molecule, and now we're shooting it with electron beams. So these electron beams are like little guns, and whenever your electron beam reaches that molecule, we're breaking that molecule into small fragments. And these small fragments are charged fragments. And now they have positive charge on these small fragments. And depending on where you break that down, you have ions with different sizes or different mass. And when those mass went over that curved tube in that machine with a magnet around, and because they're charged, they will feel the attraction force from the magnet, and then depending on their molecular mass, depending on their mass of their fragments, it will reach your detector at different time. And by looking at how much of these fragmented ion reach your detector, and also by looking at what's the time they reach your detector, we can get an idea about what's the mass of each of the fragment, and what's the distribution, what's the relative distribution of those mass fragments. All right? So these are the theoretical background. I'm not going to test you on it, but it's nice to know what is happening inside the machine when you're actually using it in lab yourself. All right. Now, for us, what we care about is how exactly are my molecule break down into smaller fragments, and what kind of information we can get by looking at these fragments. So here are some of the general things to keep in mind. The first thing first is you start from a random molecule. You can always imagine just by shooting it with one electron, you can get by shooting it with electron beam, you're knocking off one electron, and you end up with a molecule itself, just with a positive charge. So that is called a molecular ion. So what we're doing is electron beam gun is just knock off one electron from your entire molecule. It's not from any specific part of your molecule, just one electron. So naturally, by knowing the mass of your molecular ion, we can get information like molecular mass of your molecule. Now, that is one of your largest peak, or not the largest peak, but the peak that's heaviest if you think about, because that's a molecule you have. If you just knock off one electron, the heaviest possible peak you can get is likely to be your molecular ion. Now that molecular ion can also undergo further fragmentation, and we'll go over some of the fragmentation pattern of organic molecules later on. And the other thing to keep in mind is mass spectroscopy or mass spectrometry give you exact mass of every naturally occurring isotopes. So the machine doesn't care whether you have a carbon-13 or a carbon-14, or whether you have a chlorine-35 or a chlorine-37. What the machine does is it breaks your molecule into small pieces, and it measures its absolute mass. So whether or not it is an isotope, the machine doesn't care. So let's see one example of the mass spectrum giving you isotopes of a specific molecule. So the example we're looking at here is chlorine, so Cl2. So that's a one chlorine molecule with two chlorine atoms. Now it's just a diatomic molecule, so the fragmentation pattern is relatively straightforward. First of all, you have the molecular ion. Again, the molecular ion just means your molecule loses one electron and forms this cationic form. It's a molecule with a plus charge. That's your molecular ion. And further fragmentation of the molecular ion will form just a chlorine dot or a neutral chlorine atom and a chlorine plus. Now this chlorine, neutral chlorine is not going to show up on your mass spectrometry because it is not charged. Remember when it's like going over that tunnel, only the charged particles will get affected by that magnet and show up on your detector. So neutral species does not show up. And then we can also see the peak for a chlorine plus. So these are the two peaks we expect to see on the mass spectrometry. And here is the mass spectrum. It is surprisingly more complicated than you originally expected, right? We only have two possible fragmentation. We have Cl2 and Cl+. So in this case, what we have on this diagram, let's just go over it slowly in how to read the diagram and how to get information out from it. Again, for any diagram, we start by looking at its x-axis and y-axis. So on the x-axis, we have this m/z. What this means is the mass to charge ratio. So for all the species we're caring about in our class, we're talking about charge being a +1. So this mass to charge ratio is telling you the exact mass of that specific group or specific atom or specific fragment or specific molecule we're talking about. So the x-axis is telling you information about the molecular mass or atomic mass of that fragment. Then on the y-axis, that is our relative intensity. So that tells you how much of those fragments reach your detector. Note that we're talking about relative intensity. So the reason it is called relative is we always define the largest peak to be our base peak. Or the most intense peak. So in our example here, the base peak is at 70 MZ, M/Z. All right, so the largest peak is defined to be the most intense peak, and everything else are relative to that base peak. So relative to this base peak, we have 83 of the signal at MZ equals to 35, etc. Now that's what the y-axis and the x-axis, y-axis and the x-axis mean. And now let's look at each of these peaks and see what kind of chemical information we can get by looking at the mass spectrum. Now I already highlighted the numbers on each of these peaks. You can read the x-axis and you'll see that's where those numbers are. Remember, we're talking about this molecule. Now you know it's chlorine, but without knowing it being chlorine, if I tell you this is a diatomic molecule, only have 2 atoms, then you can look at the atomic mass and derive information. All right, so atomic mass here is 35 or 37. It has 2 different isotopes, so likely to be chlorine. So 2 different ways to analyze the problem. But the other way we can ask you to do is to assign the specific fragment to each of the peak. So if we put the assignment of the peak on this diagram here, what we have is here at the 35, we have the chlorine plus, but only the chlorine 35 isotope is showing up at that 35 MZ. And at that 37 MZ, we're getting chlorine 37. All right. So you can imagine at 70, at our base peak, we have a overall charged molecule of chlorine 37 with chlorine 35, sorry. And at 72, we have chlorine 37 and chlorine 35. And at 74, we have chlorine 37, chlorine 37. All right? So that's assigning peaks. But we can get even more information from reading the mass spectrum. So before we were talking about IR being more qualitative. So mass spectrum can actually become pretty quantitative, and you can get information like what's the natural abundance of chlorine 35 versus chlorine 37. So let's do that calculation here. If we read this entire diagram, what we can tell is we have 100 chlorine 35, chlorine 35. We have 83 for chlorine 35 itself as an atom. We have 64%, that's the 64 we're talking about, for the chlorine 35, chlorine 37. And we have 26 for chlorine 37, and we have about 10% for your chlorine 37, chlorine 37. So if we're doing the calculation, what's the total amount? What's the total amount, relative amount of my chlorine 35 we have? So that's here. We have 2 times 100. We have 100 times 2 plus 83. And here, 64. So that's 100 times 2 plus 83 plus 64. That's about 347. And if we're talking about the chlorine 37, so these are the chlorine 37 we have. So that is 64 plus 26 plus 2 times 10. So that gives you about 110. So you can calculate the percentage of your total chlorine 35 versus the percentage of your total chlorine 37. And, well, that's 347 divided by 347 plus 110 times 100%. So this will give you about 76%. And on the bottom, you can do the same calculation. It's 1110 divided by 347 plus 1110 times 100%. That gives you about 24%. All right, so the analysis of your mass spectrometry or mass spectrum can be a quantitative one. It tells you information about isotope as well. All right, so that's our first and second topic, the theoretical background. So the idea here of the theoretical background is pretty straightforward. You start from a molecule. You shoot that molecule with a beam of electron, and that molecule will crack down into different fragments. And depending on the mass of those charged fragments, they reach your detector at different time. And by looking at the time, we can derive what's the mass of each of those fragments. And using the chlorine Cl2 as an example, we went over the information you can get by looking at the mass spectrometry. So in this case, we can get ideas like what's the relative natural abundance of isotopes? What is the fragmentation pattern, right? So this one is 70, this one is 35. So naturally, you know your chlorine can break down into, well, chlorine plus and chlorine dot. Or you can do it vice versa. As I give you the fragmentation pattern, can you predict what that final spectrum look like? All right, any questions before we move on? Nope? Okay, let's keep going. All right, and then let's think about the fragmentation pattern of organic molecules. So, just as a reminder, what we're forming when we're doing the fragmentation, again, what we have is you start from a molecule, a neutral molecule, you shoot it with electron beam, you end up with a cationic species, and, well, one electron leave. Or if you break your molecule into smaller pieces, you can also have smaller fragments. But nevertheless, the take-home message here is we're forming a cationic species. So in organic chemistry, we went over lots of topics before on factors stabilizing your cationic intermediate. So in mass spectrometry, the formation of more stable carbocation fragments or the breaking of a weaker bond is more likely to happen. All right. So this is the fundamental baseline we're talking about. In mass spectrometry, the weaker your bond is, the more easy it is being break, or the more stable the carbocation we're forming, the more likely that chemical bond breaking is going to take place. So that boils down to something we discussed before, that are factors stabilizing carbocations. So I'll start from a review. We went over this before. we have several factors that can stabilize your carbocation. The first factor being the more substituted carbocations are more stable than less substituted carbocation. Right, so your tertiary carbocation is more stable than a secondary carbocation than a primary carbocation. So one of the kind of question you could expect is, let's imagine we have a molecule like this, right? So depending on how you break, well, let me make it more extraordinary. We have a tributyl group. So here we have an isopropyl group. You can have a tributyl group. So which chemical bond is more likely to be break, and which fragment is likely to be your base peak? So let's imagine this random molecule I just draw. And in this case, we can break it in several different pieces. They're all like CH or carbon-centered carbocation. Now, if we break it in this point, you can imagine we're forming a carbocation that is tertiary. So in this case, formation of that tertiary carbocation is more favored. And because we're forming the more stable carbocation, this is more likely to act as a base peak for the mass spectrum of this diagram. Now, we know that here we have a CH3, CH3, CH3. You can calculate the MZ for that base peak. So for that base peak, we have 4 carbon, we have 9 hydrogen, so 48 plus 9, that's about 57. So what that means is you're expecting a big peak in your mass spectrum around MZ equals to 57. So by just looking at your molecule, you can already picture what that mass spectrum look like, at least part of it in your mind. All right, so that's the first factor. That's a quick review in factor stabilizing the cations, which is the substitution pattern. Again, tertiary carbocation more stable than secondary than primary. The second part of the review is resonance stabilization, or allele stabilization, if you may. So now imagine we start from the molecular ion of M+. So this molecule here is our 1-butane. So 1-butane, butane means we have 4 carbon in total, and 1-butane, sorry. And 1 just means we have a double bond at position 1. So now by putting this molecular ion, if you imagine we start from 1-butane, we put it into the mass spectrometry, the chances are we're going to break this chemical bond here, and one of the CH3 dot will leave. And the reason behind that mass spectrometry, or the favorability, is the formation of the more stable carbocation. So by breaking that chemical bond, we're forming an allele cation. And well, we spent lots of time talking about allele cation. You can imagine these cationic species, or the positive charges, being destabilized, or being stabilized by the delocalization of the positive charge. All right. So now in this example, what kind of spectrum we're expecting? So in this diagram, let's imagine you have your molecular ion. Where do we expect that molecular ion to be? Now we have 1, 2, 3, 4. So this is a C4H8. So we're expecting our molecular ion to be at 56. Did I do that right? Yeah, 56. And we're forming an allele cation. And where does that allele cation peak be? This one is the C3. 1, 2, 3, 4, 5, 6. Actually, 5. 1, 2, 3, 1, 2, 3, 4, 5, yeah. So this one is 36, 41. So we're expecting it to be around 41. Or the other way people tend to write these peak, they would also say this is M minus 15. So M minus 15 just means we're one of the CH3 leaves. There are two different ways to label those peaks. You can either say, hey, we know what's the MZ of the group that's leaving, or just directly label the MZ of that specific peak. All right. Now let's just do one more example here. Let's imagine we have a benzyl alcohol. So we have a benzyl group with an alcohol on the end. So the benzyl alcohol has molecular formula of C7H8O. And let's just say we're telling you you're losing a OH dot. And now can you draw all resonance structure of that cationic fragment that's coming from this process, and then predict where that peak looks like on your mass spectrum? So this one is using two different kinds of knowledge we have went over before, right? So we know we're, by losing a OH dot, what we're forming. You have a benzene ring, and then on here at the end, we have a positive charge. And there are multiple resonance structures you can draw. And let's just practice that again. So these stays the same. And let's see. All right, so just a quick practice in arrow pushing and drawing these resonance structures. And what we can say is that carbocation is delocalized over the entire benzene ring. And in this molecule, where do we expect that MZ to be? So again, two different ways you can do it. You can calculate the M plus, and we know the M dot plus would have the MZ equals to, well, 7 times 12 times 8, plus 8 plus 16. Let's see. 7 times 12 plus 8 plus 16, that's 108. And we're losing a OH minus. So the peak we're expecting it to be is at M plus minus 17, which is the mass for that OH group, or about 91. Then you can check that 91 number by actually calculating the number of carbon and hydrogen on your benzylic cation. Or you can check it vice versa. So it's safe proof. You can check it both ways. All right, so these are quick reviews on factors stabilizing our carbocation intermediate and how to use those knowledge to rationalize what are the peaks look like in your mass spectrometry. Now we have two different types of specific fragmentation pattern that I want to introduce. So these two are new and pretty specific to mass spectrometry at this moment. The first one is called dehydration. So judging by its name, dehydration just means, well, it's dehydration. This molecular ion loses one molecule of water. So what happened is, let's say on the left-hand side, this is an alcohol group. That's our molecular ion. And what happened is this part just loses, and this part becomes a double bond. And we end up expecting a peak at the molecular ion minus 18. All right, so dehydration tells you we're forming an alkeno type of fragment in your mass spectrometry, and this process loses a water. So the take-home message here is when reading the mass spectrum, you look for differences of 18 MZ. So that 18 just hinting it's likely that one water molecule is being taken away from your molecular iron. Also tells you information that there is likely to have an alcohol present in your molecule. All right, so that's the first type. That's a new type of reaction that's pretty specific, dehydration, that's in mass spectrometry, and looking for that 18 MZ of differences in your mass spectrum. The last type of possible reaction happening in your mass spectrometry is called an alpha cleavage. So alpha cleavage, what we have is now this is a carbon that's directly binded to an alcohol group with some group binded to that carbon. I don't care about those two groups. Now this bond here will be called a alpha bond. So alpha cleavage is just cleaving that alpha bond. By cleaving that alpha bond, we're losing one of your alkyl radical, or R dots. And the reason alpha cleavage is pretty unique for alcohol group is that you can form a resonance stabilization. So after that alpha alkyl group leave, you can form a carbocation that's directly adjacent to an oxide OH group. And obviously, we can draw a resonance structure in this case to put that oxygen, positive charge on the oxygen. Or in this case, what we are identifying is on the left, we have the molecular iron. On the right-hand side, we have the molecular iron minus some kind of R dots. So on the mass spectrometry diagram, one of the things you can look for are just like carbohydrate leave, like a CH3, which is 15, or C2H5, which is, 29. So those are pretty easy to identify. All right, so that's the end of the quick introduction of mass spectrometry. Any questions before we do problems together? I know it's a Friday before a long weekend. Okay, so let's do some problems together and see if we got more questions. I prepared 3 simple problems with you, and these demonstrate different kind of problems you can expect when working on, mass spectroscopy problems. The first type of question is I give you the mass spectrum, and I tell you it's a 1-butanol. Can you identify the peak that's corresponding to a molecular iron, a dehydration, or an alpha cleavage? I'll also give you the molecular structure. I just forgot here. 1, 2, 3, 4. 1-butanol. So identify the peak to the molecular iron, dehydration, and alpha cleavage. So the first thing first, molecular iron. This one we can just quickly get it. Either you're looking for a largest, the heaviest peak on your spectrum. But on this diagram, that heaviest peak is actually very not so obvious. It's easy to get it wrong. So I highly recommend you calculate the molecular mass for that molecule if I'm giving you the molecular formula. So this one is a C4H10O, and the molecular weight is 74 gram per mole. Now we go back to our mass spectrometry and try to find that 74 peak. So here's 75. And that 74 peak is actually the very, very, very small one here. I know it's super small. And there's a reason that peak is super small. And that is our molecular iron. Now, if you think about it, the reason that peak being super small is because we have an alcohol that can easily undergo either dehydration or alpha cleavage. And both processes are very favored process in your mass spectrum because both processes are forming very stable carbocation intermediate. So now the question asks you to identify peaks that's corresponding to dehydration and alpha cleavage. We might as well just write down what these reactions are. So let's look at our dehydration. So dehydration means we start from our butanol molecular ion. We're losing a molecule of water. And what we're forming is, imagine here, that's the water that's being left, and we're forming a double bond there. So what we end up forming is a 1-butane radical cation. Now on the diagram, we can identify that peak for dehydration by using 74 minus 18. So that should give us 56. Let's look at it. Oh, that's 45, 60, 1, 2, 3, that's 50, 55. We're looking at 56. So yes, our dehydration is our biggest peak or our base peak. All right. And then we also have our alpha cleavage. Now, before assigning peak for the alpha cleavage, might as well just write down what does alpha cleavage mean. So alpha cleavage, we're talking about the same molecular ion. Now we're looking at the alpha bonds. So we're talking about the carbon that's directly attached to the oxygen, and we're cleaving the alpha position. So this is where we are breaking the chemical bonds. What we're forming by alpha cleavage is we're forming a radical, the alkyl radical, and then at the same time, we're forming the H2C OH cation, and that cation is stabilized by resonance. All right. And again, you have two different ways you can find that peak here. You can look at the molecular weight of my CH3O, which is the cationic peak here. And the molecular weight of the CH3O is about 31. And let's check, do we have a peak at 31? So that's 30, that's 31. So we have a big peak here. And that's corresponding to your alpha cleavage. So pretty straightforward. We give you the molecular structure, we give you the spectrum, and assign peaks to specific transformations and to specific type of peaks on your mass spectroscopy. All right. One more type of example. We can do it reversely. We can give you the molecular structure and ask you to predict the MZ of the base peak of your 2-hexene. So we're talking about prediction of the base peak. So essentially what that question is asking for is at which position we cleave that carbon-carbon bond, we can get a stable carbocation intermediate. So the way to think about it is we have two different allylic bonds. Well, this is the only allylic bond that can be cleaved to form that allylic cation. So we can cleave that allylic bond. And what we end up getting are structures. The allylic cation that's stabilized by delocalization. All right. And now let's think about it. What does this diagram look like? We know that the allelic cation will be stable. It's asking us to predict the MZ of the base peak. So for calculating the MZ of the base peak, again, you can do it two different ways. But for counting the number of carbon here, 1, 2, 3, 4. So that is my C4H 1, 2, 3, 4, 5, 6, 7, C4H7. So our MZ is about 55. So when encountering this kind of question, when we're asking you to predict the MZ of the base peak, essentially what we're asking is at which position you can cleave that carbon-carbon bond to form a stable carbocation. Whether that carbocation is favored by delocalization, by the tertiary versus secondary or primary, or by alpha cleavage or dehydration. But I won't ask you relative peak of dehydration and alpha cleavage. That really varies. Question? You're just calculating this one. So 48 plus 7. Oh, 55. I didn't do that wrong. So yeah, you're just calculating the molecular mass of this fragment we're talking about. Yes?
If you have a carbon attached to OH group and two carbons attached to that, is there a specific one that we're supposed to choose for alpha cleavage?
Well, both of them will be cleaved. You'll see two different peaks. Yes? Alpha cleavage? Alpha cleavage, just say this one is a carbon that's directly attached to your alcohol group. Then the adjacent carbon-carbon bond is your alpha carbon-carbon bond. All right, and let's see one last example here. Now we give you the mass spectrum of the 2-bromopropane. Can you explain the origin of these peaks at different MZ? So now we have the molecular structure of C3H7 bromine. And again, MZ is very good. Well, the mass spectrometry is very good in identifying halogens like chlorine, bromine. These are halogens with stable isotopes. So their mass spec will show a very special pattern. Now, if we look at what the question is asking for, it's asking you to rationalize the peaks as 122, 124, and also 43. And can you estimate can you tell what's the origin of these peaks at about at these MZ, and also estimate the relative ratio of your bromine 79 and bromine 81. So now we look at it. In this molecule, we have C3, so that's 12 plus 3 times plus 7 for hydrogen, and plus either 79 or 81. And you can do that calculation to find out that 122 is the molecular iron with bromine 79. 124 is the molecular iron with bromine 81. Right, so that's by simply calculating your molecular weight. And what we can get, looking at this diagram, is that's our 124. That's my bromine 81. And the 122. And that's my bromine 79. Now we have a big peak at 43. That's our base peak. And this peak doesn't have any stable isotopes associated with it, with itself. So that's a hint in which bond we're cleaving to form the fragment at peak 43. So again, the reasoning here is this 43 does not have an isotopic peak like we expected, because we look at 122 and 124, they're about 1-to-1 ratio. So now we look at the 43 peak, it doesn't have any isotope associated with it. So what we're talking about is likely this peak is formed by cleaving this carbon-bromine bond, and we're losing a bromine dot, and we're forming a carbocation radical here, a carbocation intermediate fragment here. So that carbocation fragment has the molecular weight, well, C3H7, so that's 36 plus 7 gives you 43. So that's where our base peak is. And the last question is asking you to estimate the relative ratio of these two isotopes. So this is what I mean by you cannot analyze all peaks in your mass spectrum. So now just use these relative peaks to estimate what they look like. But if we have like bromine 2 or like chlorine 2, that you can do quantitative analysis. But when we're looking at organic molecules, the mass spectrum of the organic molecules are typically pretty complicated. So now we can just say that's about 1-to-1. So whenever I say estimate, you should just give me an estimate, like a relative ratio, about 1-to-1 is good enough. But if I say calculate or quantitatively calculate, then you need to do whatever we did before for the chlorine 2 minus and actually calculate the natural abundance. All right, that's all. Looks like today is pretty straightforward. Let me know if you have any questions.